There we are. So welcome everybody to this second AtlantOS Ocean Hour on democratizing ocean observations through low-cost technologies and citizen science. So the first one was held in September. Correct me if I'm wrong, but I'm pretty sure it was late September last year and was quite a success. So we decided on a follow-up. And here we are. You can watch that recording from the first event on the AtlantOS website. The AtlantOS program aims to advance sustained ocean observations at the Atlantic basin scale by actively supporting collaborative partnerships between observing networks, data, and information systems and the wider user communities. The reoccurring AtlantOS Ocean Hour webinar series is scheduled to take place every other month. This event is really an opportunity for community engagement as we develop the All-Atlantic Ocean Observing System. I'm Patrick Orange. I work at the Swedish Meteorological and Hydrological Institute. I'm the manager for international ocean relations, working with projects and programs mainly related to oceanographic data. I'm on the AtlantOS steering committee, and together with my colleague from Ifremer, France, Lucy Cocompo, we run this activity on low-cost technologies and citizen science. Lucy, I know you're on a very busy, noisy train, but maybe you just want to give us a little wave to say, there you are. I don't see that wave, but I assume it's there. Mariana, can you please introduce yourself?
Oh, there you go. There was a wave.
Good.
Sure. Hi, everybody. Great meeting you. Glad you guys are all here. I'm Mariana Rocha de Souza. I am right now a Canals Fellow, finishing my fellowship at NOAA at the Global Ocean Monitoring and Observing Program. And one of my portfolio is the AtlantOS. So like I lead like the coordination for the AtlantOS Ocean Hour.
Great, thank you. Anne.
Hi everyone, I'm Anne Zinken. I was a Canals Fellow. Now I'm in the same office at Mariana as a program manager, and I'm managing the AtlantOS program. And just as a quick heads up before I forget, for everyone who's here, I'm also working on the observations coordinating group under Goose, and together with Patrick and Lucy and some others, we are organizing a low-tech workshop in person in June, on June 2nd. So keep an eye out, please, for some emails about that. We'll be advertising that workshop in the next couple of weeks, hopefully. It'll be a full-day workshop on June 2nd in South Africa, and it'll be hybrid. So keep an eye out for that.
Exciting. Everyone's welcome to join us on that one. So today's AtlantOS Ocean Hour will focus on low-cost technologies and the use of citizen science for ocean observations. There is a lack of in situ surface and subsurface data, in particular in the coastal and shelf seas, but also in the deep seas. And cost-effective ocean and coastal data are really needed to, among other things, help in the understanding of the role of the oceans in Earth's climate, and so be able to make improved estimates of how it will change in the future. There are new emerging communities collecting oceanographic data in these data-scarce regions, which can complement today's ocean observing networks. So we're here from a couple of these here today. Our four speakers will present in 4 short 7-minute presentations, followed by a 30-minute panel discussion. This session will be recorded, so please keep your microphones muted. And if you feel like asking questions, please use the chat or raise your hand at the end of the 4 presentations. Mariana, you will keep track on the time for us. Great. So without further delay, let me call out our first speaker, that is Fernando Lima, group leader at Biopolis and heavily involved in CCT Bonn, the Atlantic Ocean Coupled Coastal Temperature and Biodiversity Observation Network. And over to you, Fernando.
All right, well, thank you. Thank you so much for the invitation. With this impending climatic and biodiversity crisis, there is a need to understand the mechanistic relation between climate and biodiversity. The problem is the scale. And as you can see on this three pictures, the environment is extremely variable across all sorts of habitats, and the species cover or distribution is also species cover and distribution are very heterogeneous as well. Each one of these images would fit in a pixel of a satellite picture. But we need to go further and measure these patterns at the scale of the organisms. And we use intertidal, so the region between high and low tide, to study this relationship between climate and biodiversity. The intertidal is a great model for that. It's inhabited by marine organisms that have to withstand terrestrial conditions. So, and in the intertidal, as you can see on the left, there is this huge variation in temperature. This is a thermal picture, and between the blues and the reds, there's a difference of 10 degrees or 15, and in many occasions, this reaches 20 or 30 degrees over a couple of hours. The other issue is to measure biodiversity. As you can see on the picture of the right, it's immense. And it's very hard to measure across large scales with precision. So how can we do these two things at the same time over very large scales, but maintaining the local scale? That's our challenge. So we developed two sorts of technologies. One is the envelog. One are the enveloggers that you are seeing here. This is to measure temperature. And so temperature is a essential climate variable. That's why we are measuring it. These loggers have an autonomy of more than 15 years. They are really robust. They can withstand 1,500 meters of water pressure, for example. They are very cheap for what they do. And importantly, they have this simple user interface with a smartphone. The communication is powered by energy harvesting from the phone. So we don't use any energy broadcasting the data to the phone. And they allow us to do this deploy and forget strategy, to have this deploy and forget strategies to set up locations or monitoring locations, and then just return years later and retrieve all this data. The trade-off is that this is non-real-time data, and we need to go there and actually touch with the phone on the loggers to retrieve the data. They offer standardization, and this is what we need for this project. They have been deployed in land, ocean, in tropical regions, in polar regions, and they facilitate this distributed effort. Because they are very easy to deal with. They allow us to build these large scientific networks. We are now starting to include citizen science, and they can be regarded as well as time vaults because they are so cheap that you can put them in one site and return later and have a huge chunk of data. As for the biodiversity, we are developing an app, and the main thing of this app is that it allows us to decouple field data acquisition from taxonomic identification. So the app is actually our eyes and ears all over the world. Other people can collect the data, and we can process the taxonomy of that data later. It's a way of simplifying expedite fieldwork. Distribute the fieldwork by a lot of people, include people with a minimum training. And the species IDs is always done in layers, which are not destructive. So all these identifications can be rolled back, can be revisited, can be implemented in artificial intelligence pipelines. And this uses the phone's sensors to collect metadata that are automatically embedded in the picture. So pictures never lose who took the picture, where the slope of the quadrant, the azimuth of the quadrant, the location, and many other parameters are embedded in the pictures themselves. So with this, we are building this coupled coastal temperature and biodiversity observation network. This map are the locations where it will be finally implemented. Now it's only in Europe and North Africa. We started just last year. It will be the largest of this type on Earth. It's already fully funded. It has these 160 coastal sites. It includes both sides of the Atlantic. We will be collecting hourly temperature and early biodiversity surveys for at least 1 decade. It has this distributed architecture with many collaborators, and we will little by little start incorporating citizens in the network. It's completely open data, and again, standardization is a key factor here. I don't think I have much more time, but just to say that we are focusing on the resilience, spatial comprehensiveness. So going from small scale to large scale, standardization. This is collaborative network with fair and open data structure. And as I said, it's expandable and AI ready. We started in 2022. In 2023, we are going to deploy in many sites across the North Atlantic, and also some in the South Atlantic already. And we hope to finish this by 2024, and we hope to have the first data online still this year. Just to finalize some pictures, this is us deploying
this is
some
7
of
minutes, just to remind Fernando.
Okay,
but
just a few pictures and it's over. These are some of the loggers being deployed on the shore. It's so easy that even children can download the data, as you can see here. And this is the biodiversity survey app being used by a collaborator of ours in Cape Verde already. This is a citizen already using this to capture biodiversity in situ. And just to finish up, if you want to reach me, you can find more about all this work in coastal warming, our website, also Electric Blue, which is our startup that produces these loggers. And you have my email and Twitter there. Well, thank you.
Oh, that's fantastic, Fernando. Thanks a lot. Good start, good energy for this session. So let's move on. Let's go to Fredrik Gustafsson, or Fredrik, depending on if you're in Sweden or elsewhere. Fredrik is an inventor and an entrepreneur at Dpod. So please, Fredrik.
Okay, thank you very much. So can you see my screen or? Hello?
Not yet.
Okay. Will you see my video or can hear me?
I always see you and hear you.
Okay. So should I press something here in Zoom then maybe, or to take over? Is that maybe?
I think there's a delay in the video. Do you know how to share the screen, Fredrik?
No, not really.
Okay, I'll chat you. So maybe we can start with another speaker and I'll send you the information about how to.
Good plan.
There's a delay.
So go ahead and mute him, and then we take it that route. And instead, Katie, hope you're ready. So Katie Croft-Bell, founder and president of Ocean Discovery League, please.
How's that look?
It's here.
We good?
No.
Can you hear me?
Yeah, I hear you.
Oh,
Okay. Can you see my screen?
No.
Really? I'm sharing it.
yeah,
There you are. Now we got it.
it's great.
Got it?
Perfect.
Okay.
Yeah.
Wonderful.
Both
Thank you.
screen and sound.
Great. Let's go. Hello, everyone. My name is Katie Croft-Bell. I was also a Knaus Fellow. And now I am the founder and president of the Ocean Discovery League. a nonprofit organization dedicated to accelerating deep ocean exploration by developing accessible systems to broaden the community of those who explore and understand the deep sea. Before I get into some of the things that we're working on, I think it's important to understand the sheer magnitude of the challenge of deep sea exploration. So the surface of the Earth is about 510 square kilometers, and we all know that 3/4 of that is ocean, and 2/3 is deep sea. So 334 million square kilometers is greater than 200 meters depth. Now, the National Deep Submergence Facility here in the US has been exploring the deep sea since around 1972. And according to their records, their tethered vehicles have traversed about 15,500 kilometers of seafloor. Being very generous, if their visual swath was about 10 meters, that means that over about 50 years, this pretty well-funded facility in the US has covered about 155 square kilometers, or 0.00005% of the seafloor. So let's say there were 20 similar facilities in the world using tethered vehicles for the last 50 years. France, Japan, the UK, many other countries have these kinds of vehicles. We can extrapolate a little, and we would have then seen just over 3,000 square kilometers of seafloor. So what does that mean? Well, I live in Rhode Island, the smallest state in the US, and it's a well-known standard unit of measure and roughly equivalent to 3,100 square kilometers. So with 20 NDSFs over 50 years, perhaps we would have covered about the same area as the state of Rhode Island. And to pull back a bit, you can see what that means on a global scale. So what would it take to see the entire seafloor? Now, at the current rate, with just tethered vehicles, not talking about AUVs, it would take 100 years and 1 million similar facilities just to see the seafloor once, not even including the water column. And with a budget of about $10 million per facility per year, that totals about $1 quadrillion, or 10 times more than the global GDP. It's crazy. But even if I'm off by an order of magnitude or 2 or 3, the point is that the current tools are wildly insufficient for the task at hand. And it's exactly the reason that we need to invest in lower cost and far more efficient technologies to explore the deep sea, just so we can get a baseline of what's there for the first time. In addition, only the wealthiest countries, organizations, and individuals have access to these kinds of tools, especially in Northern America and Northern Europe. So my team documented this disparity in the 2022 Global Deep Sea Capacity Assessment, which is based on research and survey results of 186 countries and territories worldwide. And you can see the link down the bottom there. I can put it in the chat too when I'm finished. So our challenge then is that our limited understanding of the deep ocean stems from today's inefficient, expensive, and inequitable approach to deep sea exploration and research. So our strategy at the Ocean Discovery League is to deal with the 3 bottlenecks that we've identified that create the highest barriers to exploring the deep sea. So the first is developing low-cost sensors and systems to bring down the cost of data collection. Next is accelerating data analysis capabilities to make processing more efficient. And finally, we bring it all together through training and education programs to build deep sea capacity where it doesn't currently exist. So one of the systems that we've developed is called Makanu, or Coconut Eye in Hawaiian. It was developed with the Polynesian Voyaging Society based in Hawaii. Makanu can go to 1,500 meters and collect video and still imagery, as well as GPS, temperature, and depth. It costs less than $1,000 in parts. It's small, lightweight. This is one here, and can be deployed in just about any configuration you want. It also has a very easy to use graphical user interface, and you can upload your data directly to an online annotation system called Tater wirelessly without the need for internet connectivity. Makanu was created in a collaborative design process with about 20 marine professionals worldwide, many of whom now have units they're using for testing and their own data collection. In parallel, we also developed a more modular Lego-inspired system called Wayfinder that allows a user to sort of mix and match modules to create whatever kind of system you want. You can click on a CCTV or an altimeter or develop another kind of module to go in one of these kinds of housings if we don't have what you need already. So we're using lessons learned from both of these systems for future development to make data collection in the deep sea both easier and less expensive for users to be able to explore. We are also working on a number of projects to accelerate data analysis, because once we start throwing lots and lots and lots of data collection systems out in the ocean, we're going to need to deal with this data. So FathomNet is one of these projects. It's an open access online database of expertly annotated images for machine learning analysis of underwater imagery. Another is the Ocean Vision AI portal, which will be an easy to use end-to-end solution for uploading video and detecting organisms within that video automatically, essentially an easy online way to use tools like FathomNet. Much of this work is being done with Kakani Khatija at the Monterey Bay Aquarium Research Institute and many other partners worldwide. And finally, the technology alone cannot solve the massive equity problem that we have in deep sea exploration and research. So we're working with many partners to create opportunities, training, and financial support for people to get the resources they need to explore the deep sea anywhere in the world. In summary, equity is the key to protecting the wonder and health of the ocean. The emergence and you can see throughout these talks, expected proliferation of low-cost sensors and systems combined with the power of cloud computing, AI analysis, could widen the gap between those who have access to the deep sea and this type of data and those who do not, which will just exacerbate the existing inequities. And only by making the tools and systems significantly more accessible, efficient, and inexpensive will we make meaningful progress toward exploring the deep sea. Thank you.
Fantastic. Thanks a lot. That was another inspiring one. I'm taking notes here, and there's a lot of things. So I have the feeling I'm going to have to come back to each and every one of the speakers later on. Mariana, do you think I should move on to Cooper? And we go for Frederick at the last, right? So let's move to Cooper van Vranken. Cooper is the founder and director of Bering Data Collective. Over to you, Cooper.
Thank you very much. All right, let's see if we can get the slides shown and presented smoothly.
Getting there.
Is that
yeah.
Looks good to everybody? Okay. All right. Thanks very much, Patrick, and thanks for having me. So we just did kind of a strategic branding session and came up with this as our vision, enabling the thriving future for our blue planet by democratizing ocean data. So, the timing couldn't be better for this session. So, thanks very much for including me. Starting from a really kind of zoomed out perspective on why what we're doing matters, is looking at where ocean data today is and is not. And so this first picture is mapping existing subsurface data coverage in the Alaska region. And really counterintuitively, there is data, not enough data, but there is data in the deep open ocean, not deep, but surface to 2,000 meters from the Argo program is where all that data comes from. So there's pretty good sustained coverage there, but then not in close to shore. In close to shore is where things are more dynamic and most maritime industries are operating, including fishing vessels. So if you can instrument those fishing vessels, it's kind of this perfect yin-yang, opportunity to fill that gap. So, this coming myself from the fishing industry perspective, I was like, oh, this is really interesting. Can anybody else use this data? And so the secret sauce, which is not so secret, is that fishing gear goes down, it fishes and comes back up. So if you send sensors along for the ride, they get a free ride down and then they come back up. And so that profiling mechanism is able to capture some of the most challenging from developing autonomous systems and things like that, parameters, temperature and salinity profiling, and complement the Argo network in the coastal regions. These sensors come out of the water, Bluetooth automatically, and then onto the cloud, so it doesn't interrupt fishing at all, which is key. And so different sensors for different fishing types. There's a tremendous diversity in what fishing looks like today. And, depending on the data requirements and the types of fishing, we can instrument most things. And then, what does this data look like? And so in this example here, we're looking at a network, which is only 4 vessels collecting data around the Ocean Observatory's Pioneer Array. Fishing collection points are in blue, and then the Pioneer Array is in yellow. So I want to show this for a couple of reasons. And then the first is really just look at that edge coverage. That's really basically impossible to do with other technologies at a long range scale. And then the second one, so looking at the panel on the right, the comparison between the fishing vessel profile and the wire crawling profile, CTD. This is among the most high resolution CTD profiling systems in the world, and it's the match is spot on. And so to me, this data quality and reliability, even more so than being low cost, is what I see as a key for elevating citizen science to the next level. My own personal view is that, I'd rather pay $10,000 for an instrument to put on a fishing vessel if it works reliably and produces good data than a $100 sensor that doesn't work and doesn't produce data which is trusted and usable. Looking at the bigger picture, the annual budget for this OI Pioneer Array is over $10 million a year. I'm not calling for defunding of traditional ocean observation, quite the opposite. But what I think that this speaks to is the opportunities for complementarity. We're never going to get as high resolution as those buoys, but there's no way you could achieve that coverage up and down the coast with moorings and things like that. Data management, not exciting, but super important, yet undervalued in science at large, and especially for citizen science. So I was really happy with the first talk that had such a data management focus. And so the history of this approach dates back to about 2000. The key pioneers in the US, Helmholtz, France, Recopesca, the Italian program, FUS. When I came on the scene in 2018, I kind of started talking to all these programs, informally connecting them and saying, hey, look what these folks are doing over there. And as you can see from the map, there's really quite a lot going on, and the momentum is picking up with some more recent but very, very ambitious initiatives, both in Japan and New Zealand, the Moana project. These programs each have over 200 vessels catching data and then feeding directly into operational models, and have really flipped that data poor coastal region paradigm. And they have now more data in the coast than in the open ocean. So, this is here, this is proven at scale, and it's being put to work. And so bringing together this core group, we formed what is the Fishing Vessel Ocean Observing Network, or FVON, formalizing our growing community, much in the way that traditional ocean observation communities like gliders, HF radars have come together. Ultimately, we're shooting towards becoming a network under the GEOMAR framework. And we can collaboratively work to expand the observing capabilities of fishing vessels, more parameters. Community white paper coming out shortly, and then looking towards the UN Decade of Ocean Science. There is a website, so please check that out for quite a bit of literature, and then more to come on there. And then our role, I'm the chair of FVON, but our role is a little bit differently. I'm technically not an oceanographer. And so coming into this space, I realized that we could have the biggest impact by focusing on that space between oceanography and industry, and serving basically to translate culturally, but also technically. And so we're a private startup, which enables us to move quickly and in an agile manner and operate anywhere anyone needs our help and needs data and needs that support for science. So we roll up our sleeves and make it happen, getting the proper sensors for the local fishers and data requirements, lots of data management, stewardship, all that fun stuff. And then in making this presentation, it's interesting to reflect that, I think now we work just about equally for science as we do for fishing industry. And that fishing industry data collection is growing faster and faster than the science funded. And this to me speaks to those data win-wins. And this has been something that we were just looking to cultivate and then ended up doing it to a point where, you know, they want the data before science does. And so we facilitate data in a lot of different regions, especially in the Atlantic, and kicking off some things in Ghana that'll be really exciting and really speaking to democratizing that.
Copper, 7 minutes. Just to, yeah, you're good.
So last slide, sorry, going a little bit over, but thanks very much. And, you know, to me, this is really about, especially the convergence of science, citizens, you know, putting it all together. And I think there's tremendous potential there. So thanks for having this.
Thanks a lot, Cooper. Thank you. Good one. Let's give it another try with Frederick. Let's see if we can get him up and get that presentation running. There we are.
Hey, can you see something?
Yeah, just put it in. Oh yeah, there we are. Both slides and you. Excellent.
All right, great. Okay, so my name is Fredrik Gustafsson. I represent Sensoid Technologies. We're a private company. We don't really have a science focus, let's say. We work with game fishing. So it's fishing, but not really the same as Cooper. So we make some attachments really that you can put straight on the game fishing line. This is our sensor. We call that the D-pod. This is the electronic part of it. It can measure temperature, depth, light, and turbidity. Depth and temperature, pretty okay quality data, I would say, I think can be calibrated and so on. Light and turbidity is a bit less so, I think, more experimental, let's say. It can still be interesting for game fishers, though, to understand light conditions and things like that, but from a scientific point of view, maybe less valuable. So the idea is that you have this straight on your fishing line. It's low cost. This is around $200. We also have a number of attachments you can make of it. We sort of focused on trolling fishing. That means you are towing your lure at a speed. This can be quite tricky because of the buoyancy, everything is pulled to the surface at speed. So you need traditionally very heavy weights. So we have an attachment to our logger, which is called paravane. This is using hydrodynamic forces to pull it down. So since we have measured this quite well, and together with the depth sensor, we can predict exactly where it's going to be at different speeds. So yeah, the idea is that the fishing game fisher puts the lure, as you can see on the right here, a few meters after, and then this can be used to control at what depth you're pulling your lure. It's high speed stable, very cheap. It's just a plastic wing. We can pull this around 10 knots, but it depends on the depth depends on the speed very much. The higher speed, the less depth you get. So, you know, usually a lot of fishermen are actually using this today when they are game fishing. Different types of paravanes is quite common. I think this is one of the first, at least, the only one I know of that you can predict through an app, basically where it's going to be at different speeds. Yeah, so there's a real added value for a game fisherman. Also, we are measuring data here at the same time. Okay, yep. So the paravane, basically, this gives you almost real-time data. It's connected to the smartphone. So once you retract it, it's automatically connected to your smartphone, and the data is uploaded to a cloud database. You can then access the data from your phone, yeah, so that's sort of near real time. There's no GPS position that's taken from the phone. So obviously when you're underwater or somewhere else, it can be rather inaccurate. We try to encourage our users to share data through the database. So you can share basically with other people, you know, on a map, sort of where you have data. Also, we only work with the game fishers, catch and release. We don't work with commercial fishing at all. Yeah, so maybe the value here could be, from a science point of view, sort of hard to get data from shores, small lakes, rivers. Our users are all usually very close to the coastline. So where I think automatic systems, maybe commercial fishermen are not operating much. So there is maybe a data gap here somewhere. I should say we are not actively today really sharing any scientific data or data with any scientific community. This is purely for our users and our use so far. So this is what it can look like. This is close to where I live, Mälarhöjden in Sweden, Lake Mälaren. You can see a lot of dots here. You can click on one of these points and you get a depth profile, temperature, depth. You can see light and so on, what we actually log. You can also get tabular data like this that you can copy into Excel, whatever you want to do with it. Yeah, okay. Thank you for that. It was maybe shorter than 7, but.
Well, we didn't have to push you, did we? Perfect. Yeah. Mariana, I've been looking at you, but you look happy, so that's a good sign. Thank you, Fredrik. Thank you really to all the 4 speakers. Very inspiring. Like I said, I have like a page of notes per speaker here, so there's going to be a lot to cover after here. I suggest let's go straight into some questions. Mariana, have you kept track of the ones in the chat, or should we go there and have a look?
I think the ones in the chat have been responded. So we can come back to them if we don't have any question. There is no question like right now, but we can ask questions ourselves. Like, yeah, everybody's encouraged. People online, type your question, or you can raise your hand and ask directly to the speaker.
I can start with the question. Well, one of them I have here, and it goes to every one of you actually. I understand that most of you do make your data available for reuse, correct? That is to make it available for others to discover and use, right? Is there anyone who has restrictions to these data, or are they all freely available? Cooper, try it out.
Okay, we're probably the most. So we work with folks like EMODnet, Copernicus Marine, and so we do serve a lot of data publicly available and everything like that. But then we also have data where, you know, industry funded data and they're not comfortable sharing it yet, or we kind of work step by step to get that data available and kind of meet anyone the kind of halfway that's necessary. I would say, though, most of our data is publicly available in some form. And then there is also kind of GTS or Copernicus Marine in situ TAC, like kind of the different channels that you're doing. So sometimes you can't get the raw data, but you can get it put into these more standardized formats.
Yeah, because you already mentioned data aggregators such as EMODnet in Europe, Copernicus as well. They are really screaming to get this kind of data and make that available. So that's great. Good one. Let's see. What do you have, Mariana?
Renelis, would you like to ask your question? Renelis had sent a question on the chat. If she's not here, I can read. I think the question was to Cooper. Have you reached out to South American, African fishers to consider involvement with FVON to collect data in the South Atlantic?
Yes, we're all about it. But if you are down there and want to talk, I'm really excited about that. To me, I'm more excited about working in regions like that where, well, I don't know how to put this. The conversations are very different there versus in the US or in Europe. We still are super data poor up here, but in some of those regions, can't afford gliders, can't afford buoys, you can't afford anything. So it's like, okay, let's go, let's do this. And so to me, that's really exciting. And it's a very clear kind of benefit right away. And both, so I think in South America, the only place we're starting to talk is Peru and Chile. But it would be great to come over to the Atlantic side. And then actually Carles, the co-founder and CTO, is in Morocco right now. There's a big industry conference happening.
I have one question more like I would like to hear from everybody. I think like a few, or maybe each one of you touched on this, but maybe just emphasizing like who are the people that are actually deploying these instruments? Like what's the public, and how do you train them to be sure that data is actually validated?
Can I answer?
To each
Yes.
person.
Can I answer? In our case, it's we are deploying the loggers at this phase with the help of local collaborators. So in our case, the effort is all put up front, and the logger deployment is the critical phase where we want to make sure that the loggers are facing the right directions and at the right tidal height and so on. And so in this initial phase, we are kind of collaborating more closely with the people, locals, which at this point are scientists. And we are going to the places where they are already going every year. So then they can just continue taking care of the instruments and downloading the data and doing the biodiversity surveys. At a later stage, when we have all this properly documented and the process is completely fine-tuned, then we will be able to rely on other people to actually deploy the loggers themselves.
What about you, Kati? Like, how are the instruments deployed to the deep? Yeah, how is it deployed?
Yeah, great question. We have right now about 20 or so cameras in the hands of some of our test users, collaborators that we've been working with over the past few years to create the systems, and they've been deploying them in a lot of different ways. You saw a sort of PVC lander that one of the users created. Some people have strapped them onto other vehicles so we can compare data between some ROVs or towed systems to go along with the data they're collecting. We provide online support. So sometimes we're shipping cameras and things back and forth. So if something breaks, we can help fix it. And yeah, it's all of this work has been done during the pandemic. So we've not actually worked with anyone in person. All of it has been remote support and training, and it's super easy to use. When I got mine for the first time, I think 5-year-old at the time was running around the house taking pictures of all of our animals. So it's pretty easy to use. Right now, we've actually just built another 6 cameras and are trying to set up a sort of lending program so that we can make them more available to more people. And to do that, we're also looking at, what kinds of, manual training videos, what kinds of other resources people are going to need who haven't been working with us since the beginning of this, so that we can make them more available for people to be able to use and learn all the lessons that we need to learn to continue making it scalable too, right?
Thank you. What about you, Frederick?
Yes. Well, I mean, it's pretty easy to use, actually. You get the code, and once you punch that into the website, you can access all your data. It's all pre-prepared, let's say. All our data points are basically pre-prepared when we ship the unit. We calibrate temperature before we send it, yeah. It's very easy to use. I mean, you put it in the water. All you have to do is set so that it understands the Wi-Fi hotspot, and so that's it. then it's automatically uploaded to the Amazon Web Services once it's retracted from the water.
Mariana, there's a follow-up there for Frederick from Julian that maybe could be good. What would it take to make your data available to the open public scientific community? Frederick?
I think some support to understand metadata and how to actually connect our database to something else. Because of course we are collecting the data, but we have no experience in how to get it out from our database, you know, onto some other platform. So yes, support, I think.
Yeah, good. Mariana, they're pouring in.
Cooper, would you like to respond quickly to this? And then we jump to the next question, like how is the data deployed? I think you work with Fisherman, you have touched on this, but just giving you the chance if you'd like to say something.
Very briefly, it's really kind of co-design. We communicate the requirements, but then the captains who are deploying their gear, they kind of know the best way to mount it, to understand how to get it in a protected way that's not going to get mucked up or anything like that. And then one point, kind of what Frederick was just talking about, ERDAP is kind of a key thing as an emerging network for getting your data and making it, putting the right framework for making it compliant and things like that. That's there's a lot of us fans of ERDAP, but just had to put that one out there.
This could be a future AtlantOS Hour on ERDAP. Yeah, I think that this is a really nice one. We already rehearsed it in Sweden the other week, so we can help you out.
Leslie, would like to unmute yourself and ask the question?
Yeah, sure thing. Leslie Smith here. I'm the project director for the Deep Ocean Observing Strategy. So, of course, I want Katie's answer to this, but all of you shallow water folks as well. What do you guys feel is the biggest challenge or impediment towards large-scale use and deployment of low-cost sensors into the global ocean observing system? So how do we go from startup to broad-scale implementation, making this more the norm than the exception?
I think the first challenge is we just don't have the tools yet, right? We need to create whatever those tools are, and make sure that they're low cost enough that you can. And I think that scale will help us get to lower cost. A lot of these tools, and Leslie, you well know, you make one of them, you make a couple of them, and because of that, they cost a lot of money, millions of dollars to create, a single ROV system. But if we could bring the size of them down and build lots of them, using many lessons learned that already exist, you build millions of phones and they cost a few $100s. So how can we create that sort of scalable manufacturing system so that you can bring the cost per unit down? And then we can start to talk about, like, what does the deployment strategy look like? Where do you need to deploy them all over the world so that you can get a statistically significant sample of the entire ocean, right? Because that's the ultimate vision. We're not going to be able to see every square centimeter, every square inch of everything, but what do we need to cover? And Leslie, we should chat about this because I've been thinking about it a lot. That's the question, is how do we create that? Because right now, the one ship with the one ROV going to the place for a week, that's not going to get us anywhere. It's going to take 10,000 years. And we don't have that kind of time.
Someone else want to add to that? Want to respond?
I can say that one way of overcoming that initial going over the crest of costs and scale of deployment is to get research projects that fund the initial thing. That's what we did. But that is very difficult in many cases, and we were just lucky in getting those. So I would say that having those first funds for kicking off the deployment and actually getting everything running is the biggest challenge, because then once you start collecting data and other people start seeing what you can do with so little money, then everything becomes much easier. When people see things, then they believe. But at the beginning, there's a stage where you have to make other people believe without having anything. And I think that's the major challenge.
Can I add one thing? I totally agree with you, Fernando. And I also want to bring up, at the beginning of Cooper's talk, he mentioned the Argo program, which I think is an amazing program. They've been operating for 20 years, collecting CTD data in the upper 2,000 meters of the water column, and have thousands of systems out in the world all the time. So could we create some kind of analogous system for the deep sea? I think the deep sea Argos right now are really expensive. So, can we bring those systems down and perhaps use lessons learned by Argo program and others to figure out what is that global strategy, sampling strategy look like?
Frederick, would you like to add? Cooper, go on.
I couldn't agree more kind of with what's being said. Economies of scale are super important, and we don't have that yet across the board, from instrument makers to any of this, and Argo is kind of the shining beacon of that. Fernando, that's super exciting that you've been funded at such a large scale. I ultimately think that a lot of this comes down to, we need to think a little bit differently about ocean data. And transitioning from, National Science Foundation, EU Horizon 2020, these projects that fund studies that go on for 5 years, and then the data dries up and goes somewhere else. And there are other folks talking about this too, is thinking about it in a sustained kind of operational context, much the way that weather data is funded. So that, there's a network sustained funding, and so we get this longer term understanding, and that's tricky. And the government entities have limited resources and all of that. So making that pivot, I think, is going to be challenging. But
Evandro, would you like to unmute yourself and ask your question? Sorry, Frederick, I don't know if you wanted to add something and add to this answer before we go to the next question.
Not regarding that, I think. I see some questions that have been answered. There's a quality control of your data and also calibration. Could be interesting.
I was asking if Evandro wanted to unmute himself, but I don't see him. Yeah, he had a question. Yes. He had asked about quality control. What was the calibration for most of the instruments? So go on.
You want me to speak? Okay, yes. Well, not being a scientific focus for our business, but it's still possible to calibrate. We can use to calibrate actually all our data points. There's a built-in display, so it gives you a guided calibration of 2 points, and then it's kind of linearly scaled. So that's possible, temperature and so on. Of course, I don't expect people to have a really good thermometer at home, but if you have, then it's possible. Maybe you can use ice water and maybe room temperature water, something like that. We have tried that, and it kind of works. So yes, that's what we could offer. I don't know about the rest of the sensors. It will be interesting to see how you handle kind of long-term drift in your systems.
In our case, we also pre-calibrate everything, and because we are only dealing with the temperature, so we have no turbidity, the sensor is not exposed in any sort in any way to the environment. It doesn't get any corrosion, it doesn't degrade, and so it's very stable over the time periods that we are considering. We don't measure any noticeable drift, and we can check that very easily because we have multiple loggers next to each other at each one of these locations. When they are covered by water, they must be registering exactly the same temperature, otherwise something is wrong. And we get this agreement between loggers even after 10 years. So it's pretty stable. Someone asked the resolution and accuracy. It's 0.1 and 0.2, and we don't put much effort in going further than that. I think that's enough for what we are at the scale we are looking at.
Any more there, Mariana, or should we?
There are a lot of questions in the chat.
I know there are a lot. There are a lot of them. That's my problem.
I saw another question actually.
There's
someone asking pH integration. Actually, we are looking into that. We are looking together with a German company to incorporate CO2, O2, and pH by using a plastic membrane, which changes color. So we would add, instead of our light sensor we have today, we would have a spectrometer chip that can read the color. This would be a replaceable membrane that you can then just stick on, and it's pressure resistant to a lot of bars, so that's not a problem. And we would go measure this through a light glass. So yes, so we are working on that. Actually, conductivity and salinity, I expect other people to have already. So I saw that in the question as well. If you have the CTD, then I guess you have that.
I think like I'll end with one question for each one of you. Martin had asked if anyone offered trainings and maybe some startup fundings for regions with lower technical capabilities. And I'll add to that question. So like not just trainings, but anyone that's here in the Ocean Hour or anyone that's going to watch the video online, how can people be involved? How can people get in touch?
Can I answer?
Yeah, feel free.
All right. So in our case, we have the whole program already funded, and we are providing all the loggers and even the mobile phones, everything for free to everyone that is collaborating with us. We cannot fund the traveling of people, so that's why we are choosing people that are already working on the intertidal, but all the equipment is covered. And we are, of course, we offer training for free, either remotely or in situ. As I said, in this initial phase, we are mostly going to the places and working with the people for the first time, and then after people are trained, they can continue the program themselves, having received the instruments for free.
Awesome. Katie?
Yes, sorry, I was just trying to type some things in the chat so that people could just click on links. I'll put that in a moment. A couple ways to reach out. One is just come to the Ocean Discovery League website, oceandiscoveryleague.org, sign up for the newsletter, send us a note, see what you're interested in. There is a workshop coming up at the end of February on FathomNet. So that's the annotated database for machine learning. I'll put the link to register for that in the chat. It's geared toward Asia Pacific times, so it might be in the middle of the night for those of you in Europe, unfortunately. But would be a great way to sort of start to get involved with that community. And on the funding front, we're working with the Experiment Foundation. And the experiment.com is a way for people to crowdfund funding for research projects, for science projects. And one of them specifically is focused on ocean solutions. So it's not huge amounts of money. It's like, $10,000 to $15,000. So particularly for students, early career folks who like have a great idea, but just need a little bit of money to get started. It's a great way to get that. And the Experiment Foundation has money to match people. So you raise some money through the crowdfunding, and Experiment Foundation will match it. And I'll put the link in the chat to that. They've funded about 20 or so projects, ocean specific projects last year. And so about $200,000, I think, something on that order of magnitude. So it's a great opportunity, and I'll put the chat in there. Hopefully it's helpful to some.
Awesome. Thank you. Cooper?
Yes, so please don't hesitate to get in touch with me. I'm putting links in right now too. So fvon.org is the broader kind of scientific site. And then Patrick is also involved with that. There's folks, I won't list everybody, and then you can drop me an email as well. And then we also have an upcoming session at the Oslo meeting in Palma de Mallorca in June. So it would be great to have some participation there, and hopefully some other folks are in the area. Yeah.
Awesome. Frederick?
Yeah, sorry, I'm not really following what you want me to say now.
How are people trained, and how can people get in touch? If people want to use the instruments, how can they do that?
Well, just go onto our website, deeppod.com. That's it. I think that's the best. You can reach out anytime.
Thank you.
Perfect.
Thank you all so much for being here. Thank you for all the speakers, for the amazing talks. I'll reach out to each one of you for the speakers to get all the links that you're providing here on the chat. I'll try to copy as much as I can, and I'll send it to all the participants in case people don't have time to copy everything through the chat. So I'll email everybody following up with all the links.
Excellent. There's a lot there. There's a lot of information there.
There's a lot of information there. There's also a lot of questions that we're not answering in the chat, so I can also send this to the speakers, and then you can answer them directly. Thank you all so much. This was recorded. We're going to add this into AtlantOS website, so feel free to check that out later and to advertise, and keep an eye for future ocean hours. Thank you so much.
Everyone. Thanks.
Thank you.
Thank you, everybody.
Bye. Thank you.
Bye.
Bye-bye.